the lecture notes for chapter 4. I have just uploaded another chapter 4 part 2. Okay, I am going to cover all the chapter 4 part 1, and I if I can finish today, then I will cover the part 2. So please download the lecture notes from Google Classroom. I have just uploaded. Okay, I will start the class now. Yeah, sorry? Attendance? You did not receive the link. I wait. I will attach to you. Okay, now I will continue with the lectures that I have stopped last week. Okay, I have covered some of the examples about the spice code. Okay, there are 5 examples here. So example 1 until example 4, the code given is easy to understand. Okay, it is all about the connections of the electronics components. Okay, so this one I have briefly mentioned last week. This is not difficult to understand if you know what is mean by the syntax here. Okay, so this one the example 1 until example 4, I will leave it to you to revise back. So now example 5. Okay, I will start with example 5. Okay, in these examples, consider to find the response of the RC circuit in figure 8.1a, given an input rising from 0 to 1 volt over 50 picosecond. Okay, you see the circuit here is given in figure 8.1a. This is the circuit with a voltage source, resistor, and the capacitor. Okay, this is R and C. This we call as RC circuit, okay, because there is a resistor and capacitor here. And then the resistor and the capacitor here determine the RC constant, okay, determine the RC constant. And this will actually change the curve of the RC uh, or the circuit response. Okay, this is the graph, okay, that shows the RC circuit response. Okay, as you see that this is a curve, okay, where the circuit start to rise. Okay, the input voltage start to increase. Okay, following the time that is determined by the RC component. Okay, as given here as the RC time constant of 100, this is 100 what? Ferrofarad, femtofarad. Okay, this is femtofarad, 100 femtofarad multiplied with 2 kilo ohms. Okay, this is equivalent to 200 picosecond. Okay, is much greater than the input rise time. Okay, we intuitively expect the output would look like an exponential asymptotically approaching the final values of 1 volt with a 200 picosecond time constant. Okay, so this graph shows uh, the rise of the input. Okay, it is increased exponentially. Okay, and then with the 200 picosecond time constant. Okay, and then to stimulate to get the graph based on the circuit, we can actually write the SPICE code in this way. Okay, so this is the SPICE code that is given. Okay, the statement here is with some of the syntax, okay, of the SPICE code. Okay, and you see that for parameters and models, okay, this is the configurations of the uh, configurations, parameters, and the models, okay, that I use, okay, is included and is right in this command, okay, dot options post. Okay, and then simulation netlist. Okay, simulation netlist mostly is uh, it describe the connections of the electronics components. Okay, so in the circuit there is a voltage source, a resistor, and a capacitor. Okay, so all these are the electronics components. And then with the nodes, okay, in, ground, in, out, out, ground. This is the nodes. Okay, we can actually label the circuit with the nodes given. Okay, as given in the SPICE code here, the nodes is in, ground, out, 3 nodes. Okay, so that also means that, okay, the nodes here, this is the in nodes. Okay, this is the out, this is the ground. Okay, so we can check that. Okay, so for V in, there are 2 nodes. So this 2 node is in and ground. So we can see, okay, this is in and ground. Okay, and this PWL, this is L. Okay, remember when you write the SPICE code, you want to use the pulse input. Okay, you need to make sure that when you write this command, this is not 1. Okay, this is L. Okay, and this is the pulse amplitude, okay, and the time, can where it is input to the circuit, okay, and then R1 here, it is connected to the node in and out. So here as label, this is in and out. Okay, I label accordingly. Okay, so that you can check both. Okay, the circuit and the spice code. Okay, and then the resistor here is 2K. So here is written as 2K. For the capacitor is connected to the node out and the ground, and then the value is 100 femtofarad. Okay, so to describe the connections of the circuit is not difficult. Okay, as long as you can understand what is meant by the code given here, so you know how to write it. Okay, and then to start to stimulate the circuit, of course, we need to have to include this command, some of the commands here. Okay, after we run it, what is the analysis that we want to perform and what is the output that we want. Okay, so the analysis here is the transient analysis that is to be performed on the circuit. Okay, and then the output here, if you want to observe the output, then we can plot the graph. So this is the graph, plot input and output, then dot n. Okay, so this plot indicate this is the graph that should be obtained. Okay, maybe not this graph because this is a voltage versus time. Okay, the graph can be different. The graph that is written here in the commands here is actually plot the input and output. Okay, so it's not this graph. Okay, it's a different graph. This graph is voltage versus the time. Okay, so there are two graphs here. Okay, so this is the last examples to illustrate how to write a spice code for the circuit. Okay, now is the multicolor simulations. Okay, this multicolor simulations is also one of the simulator that can be used. Okay, and then what is the purpose? And then I will briefly mention here. Okay, this multicolor simulations is a computerized mathematical technique that allows people to account for variability in the process to enhance qualitative analysis and decisions making. Okay, there are some others varying parameters. Okay, uh, that we have to consider when we want to make a decisions on the IC design and the IC productions. Okay, so the next few slides has an example, okay, to show you what and how multicolor simulations works. And okay, these simulations is a very brief topic. Okay, multicolor simulation is a very brief topic. Okay, there's only a few slides. Okay, 4 to 5 slides here. Okay, there is a case study here. Okay, this case study is to um, show you why multicolor analysis and why we need to use this for simulations. Okay, for studies. Okay, so according to the case study here, in electronics design, there are multiple varying parameters and typical design. PCB consists of hundreds of components. Okay, it is unrealistic to assume that the values are strictly unchanging in every single product PCB. Okay, the fact is electronics components like capacitors, resistors, inductors, and transistors are produced with a tolerance rate on their value. This means a 100 ohms resistor may turn out to be 95 ohm when measured. Okay, in some design, accuracy is crucial and the varying value can affect the functionalities of the circuit. To have a good idea on the probability of failure, PCB designers depends on the Monte Carlo analysis. Okay, according to this case analysis, uh, it gives a case study about the failure of the PCB. Okay, the failure of the PCB is not only on the it is not on PCB. Okay, it is means the failure on the electronics component in the PCB. Okay, so we can actually do the analysis, okay, using Monte Carlo analysis and simulations to predict, okay, the probability of the failure. Okay, in reality, we do not know how many electronics components uh, will fail and how many has defects. Okay, we theoretically or in studies we can actually use this Monte Carlo analysis to predict to do the predictions on the numbers of components that has defect or the numbers of components that can fail. Monte Carlo analysis run a series of analysis like transient, noise, and AC/DC sweep over a specific circuit by substituting the parameters with possible values from the specified tolerance. A simulations process that generates probability of risk using a mathematical model. The method provides a range of possible results based on the varying parameters that are measured in the analysis. Monte Carlo analysis is about generating predictive situational results based on distributing factors that may influence the outcome of the process. It takes into account the maximums and minimum thresholds of each parameters and randomly iterates the simulations with different values. Okay, so in the process of Monte Carlo analysis, if we want to predict the defect or the failure of the electronics components, the probability of the failure, okay, with defects, we have to include the varying parameters. Okay, the varying parameters is the input to the stimulator, okay, or is the input uh, for simulations. Okay, then based on the input, okay, then we can obtain the probability. Okay, the input here is varying with values. Okay, and then sometimes we call it it is the parameters. Okay, input parameters that can have varying values. Okay, so all these determines the outcome. Okay, of the process from Monte Carlo analysis. Okay, various types of probability distributions are used in Monte Carlo analysis. Commonly used probability distributions are the Gaussian and uniform models. The probability distributions represent how the possible outcome values are distributed and give a good pictures of the risk when presented in a histogram chart. Depending on the parameters involved, completing a Monte Carlo analysis simulations may take hundreds of thousands of iterations. Okay, since Monte Carlo is about to obtain the probability of something, okay, just now I mentioned probability of the failure of the electronic components, for examples, then the uh, output, okay, one graph we should see there is a probability distributions. We call it as a Gaussian distributions. Okay, so this graph, as you see that this is a Gaussian distributions. Okay, it use mathematical equations. Okay, the mathematical equations, when you use it to do iterations, okay, and then when it finish, and then the graph that it shows will be like this, okay, in Gaussian distributions. Okay, so here these Gaussian distributions, okay, here uh, just now I already mentioned it. According to this statement, okay, it represent how the possible outcome values are distributed and give a good pictures of the risk, okay, when presented. When hundreds of when hundreds or thousands of PCB are manufactured, you will be praying that you have spotted every mistakes and have made amendment. It is unimaginable to have a large numbers of PCBs to be defective. Okay, Monte Carlo helps to predict the risk of defects in PCB manufacturing. Okay, okay, the common method that can use to perform this Monte Carlo analysis, as I know, is to use the Excel. Okay, Excel can actually do this Monte Carlo analysis. Okay, Excel can calculate, help us to calculate, okay, the value, the probabilities values, okay, based on the equations that we define, okay, in Excel. Okay, you can try and check yourself, okay, in YouTube or in other website, okay, but I get to know from YouTube. Okay, Monte Carlo analysis can actually perform using Excel. Okay, there is another method. Okay, but I'm not familiar with another method. Okay, so that one I will not mention further. Okay, this is for your knowledge. Okay, about Monte Carlo analysis and simulations. Okay, sometimes the fluctuations in parameters can result in a fractions of the production's PCB to be rejected. Running the Monte Carlo analysis give a clearer pictures of what to expect when the PCBs are produced. Okay, so this is the last slides about Monte Carlo analysis. Okay, if you think you want to know more about Monte Carlo analysis, you can actually find it from another website. Okay, but here this is what I have here according to what I understand, so I include it in the lecture notes. Okay, okay, now I goes to the part 2. Okay, I would expect that you don't have any questions on this topic, so I will straight away goes to the part 2. Okay, part 2 is about VLSI design methodology. Okay, I mentioned before in the first chapters about VLSI design methodology. Okay, it is also means the VLSI design flow. Okay, any one of you remember what are the steps in VLSI design flow or design methodology? Okay, maybe you all got to revise back. Okay, now I go to the next slide. Okay, to show you what is the outline that will be covered under this VLSI design methodology. Okay, this is the outline. Okay, um, VLSI design flow. Okay, can be represented in three domains. Okay, they are structural, behavioral, physical domain. Okay, this design flow. Okay, to help you to recap, this design flow is actually there are a few steps. Okay, we need to perform. Okay, to fabricate and produce an IC. Okay, it start with the specification. Okay, specification and architectural design. Yes. Yes. I'm not showing. Is it? I didn't share. Okay. Sorry. Maybe I skipped. Okay. So I'm sorry. I didn't share my screen. Okay. So I repeat again. Okay. So this is the VLSI design methodology. Okay. And then the outline. Okay. Uh, okay. Under this topic. Okay. This is a short topic. Okay. So under this topic, um, the outline here, as you see, it's cover about VLSI design floor planning, and design quality. Okay, and VLSI design flow. Okay, I have covered in chapter 1 before. Okay, you will have to revise back what is VLSI design flow. Okay, just now I mentioned it start with specification, architectural. Okay, I cannot remember all, but I just state what I remember here. Okay, architectural design, circuit design. Okay, circuit design. Okay, and then there is also, before circuit design, there is also register level design. Okay, and then logic design, physical design. Okay, and then fabrication, and last one is packaging. Okay, so this is your SI design flow. Okay, now you learn about, okay, theoretically you learn about all this design flow. Okay, but practically you are now doing these two, logic design and physical design. Okay, in your lab, okay, you are now doing the lab work related to logic design and physical design. Okay, even though you are not going to fabricate an IC, okay, to package, okay, but you learn how to translate a logic design or a logic circuit to physical design. Okay, physical design is the last approach, okay, before an IC or before logic gates can be fabricated. Okay, okay, so all these VLSI design flow, they are actually represented in three different domains. Okay, the domains are the structurals, behaviorals, and physicals. Okay, so for example, physical design, it means that it is in physical domain. Okay, behaviorals can be in uh, register level design or architectural design. Okay, so later each of these domains will be described. Okay, and then floor planning. Okay, this floor planning is one of the steps. This is important steps. Okay, after logic design. Okay, the IC before it is being fabricated. Okay, other than we need to produce the physical design, we also need to do floor planning. Okay, what is floor planning? This is also will be covered. Okay, and then the design quality. Okay, design quality is about the quality of the design. Okay, uh, that determines the performance of the circuit. Okay, if the design is not good, okay, that also means that the performance that the circuit can achieve maybe is not good as well. Okay, to describe the three domains here, there is a cascade chart. Okay, this Y chart shows all the um, design level. Okay, show all the design level in the three domains. Okay, this Y chart. Okay, it allows the designer to work at various levels of abstractions. Okay, this level of abstractions, okay, I mentioned before to you, we can actually represent the chip in different level. Okay, so the levels here, okay, there are many others levels, okay, in that three domain. Okay, so they are shown spectrally in the Kasky Y chart. Okay, so this is the chart that I mentioned. Okay, in three domains, they are behavioral domain, structural domain, and physical domain. Okay, physical domain sometimes we also call it as geometrical layout domain. Okay, they are of the same meaning. Okay, why this is called as Y chart is because you see the chart here. This is the Y shape. Okay, it is in Y shape, so we usually call it as the Y chart. Okay, the Y chart illustrates a design flow for most logic chips using design activities on three different axes, which resemble the letter Y. Okay, it describes different perspectives in the hardware design. Okay, so for these three domains, okay, how can we interpret? Okay, for the behavioral, okay, these domains describe the temporals and functions behavior of a system. Okay, for examples, we HDL. This is hardware language, not high. Okay, this is hardware description language. Okay, you learned it before in your year 2. Okay, um, you use this language, okay, to write the program. Yes? No. There's no one. I'm actually watching you all because I thought you have anything. Okay. Okay, and okay, so you use this language to write the program, and then the program is about the functional behavior of the system. Okay, if you want to perform a specific operations, then you can actually use VHDL, okay, to write the functional behavior, the behavior of the circuit. Okay, there is another language, okay, that is Verilog. Okay, this is also used can be used. Okay, this can be used to describe the behavior of the system. Okay, another domain is structural. Okay, structure is means the structure of the system. Okay, a system is assembled from the subsystems. Here, the different subsystems and their interconnections to each other are listed for each level of abstractions. Okay, and then for geometrical layout or physical layout, okay, in this domain, the geometric properties of the system and its subsystem are considered. So there are informations about the size, the shape, and the physical placement. Okay, so you have learned about layout design. Okay, so you know what is in the layout design. Okay, it is about the spacing and then the width of all the layers. Okay, and the spacing and layers all is about the area and the size. Okay, of the design. Okay, it is actually composed of a transistor. Okay, so I should say that it is about the area of the transistors. Okay, that compose the feature size of the transistors that to be fabricated on the chip. Okay, for each of the domains, there are 5 levels. Okay, some Y chart show 4 levels only. Okay, so it is 4 to 5 levels. Okay, so according to the chart that I given here, okay, they are of the 5 levels for each domain. Okay, so for behavioral domains, the levels here are system levels, algorithms levels, register transfer level, logic levels, and transfer functions level. Okay, and for the structural domain, okay, the level here, there are also 5 level. Okay, it means that at different level, it describe the chip differently. Okay, the first level describe the whole processor. Okay, the structures of the chip. Okay, we see the whole thing. Okay, the processor, the chip. Okay, and then when we see the low level, a lower level inside the processor, it has aluminum. This is not aluminum. This is arithmetic. Okay, this is arithmetic logic units, RAM, and etc. Okay, and then when we look into a lower level of all of these unit, okay, they are actually composed of gates, flip-flops, latches, okay, and others. Okay, and then all these gates we can use the transistor, okay, to make it logic gates. Okay, so in uh, another lower level, so this is the transistors. Okay, in the physical domain, physical domains also 5 level. Okay, physicals, partitions, floor plans, modules layout, cells layout, and transistor layout. Okay, so now you learn about transistor layout. Okay, you can draw a transistor layout based on the transistor level schematic. Okay, and then you also can draw a cell layout. Okay, when you use the transistors to draw out a circuit, you can actually that also means that you have created a cell. Okay, you created a cell. Okay, when you can created many cells with different logic circuits or logic gates, okay, then this means that you can actually create a module. Okay, okay, and then this is all the levels in the physical domain. Okay, so I will further describe the 5 levels in behavioral domain. Okay, so this one is the 5 hierarchical levels in behavioral domains. Okay, system level. Okay, system level is the first level in behavioral domain. Okay, what does it mean? Okay, here as given, basic properties of an electronic system are determined. For the behavioral descriptions, blocks diagram are used by making abstractions of signals and their time response. In structural domains, blocks used are CPUs, memory, chip, and etc. Okay, how this system level is related to structural domain? Okay, we can refer to the Y chart. Okay, you see this Y chart again. Okay, if you see this chart carefully, there is an error and line here. Okay, this error and lines has its meaning. Okay, okay, if you follow here, okay, in the behavioral domain at the system level, okay, it means that these systems indicate the processor, okay, indicate the chip itself, okay, in structural domain. Okay, so you see this line is going to the first level of the processor in structural domain. Okay, and then it goes to the floor plan, okay, in physical domain. Okay, floor plan consists of all the algorithms, okay, all the algorithms that are operate by the arithmetic logic units and the RAM. Okay, so you see it goes to algorithm, sorry. algorithms. It goes to algorithms level, and then this algorithm levels is goes to ALU and RAM. Okay, and then this ALU and RAM is actually draw out in a module layout. Okay, and this module layout, if we go to see uh, in depth, okay, inside the modules, it is actually consists of the register transfer. Okay, and all this register transfer has the gates, flip-flop, and etc. Okay, and then it goes to the cell level, cell layout, and then logic. Logic means the logic functions or Boolean functions. Okay, this logic of Boolean functions can represent by the transistor in transistor layout. Okay, so this is how we can relate all of these design representations in three different domains. Okay, so the descriptions here that I will cover. Okay, uh, it is all have the relationship. Okay, they are related. Okay, they are related at different level in three different domain. Okay, so for this algorithmic level, okay, it is defined by the definitions of concurrence algorithms. Okay, this concurrent algorithm means that the algorithms can be written or defined, okay, using signals, loops, variables, and assignments. Okay, in structural domains, the blocks refers to the ALU. Okay, and then at a register transfer level, okay, it is a more detailed abstractions levels on which the behavior between communicating register and logic unit is described. Here, data structures and data flows are defined. Okay, in the geometric view, the design step of the floor plan is located. Okay, another level is a logic level. Okay, logic level, it is means that the Boolean function, okay, the level at which the circuit is represented using a logic functions. Okay, so this logic function is described in the behavioral perspective by Boolean equations. Structurally, it displays the gates and flip-flops. Okay, in the geometric domains, the logical level is described by standard cells. Okay, so if you have a read on the descriptions given here, okay, it is all about the Y chart, okay, that I described just now with this Y chart. Okay, okay, when you do the revisions, you need to refer back to the Y chart, okay, for these two slides, okay, the descriptions in these two slides. Okay, uh, okay, so that is all about the descriptions for the Y chart. Okay, it's also a very brief subtopics. Okay, and the next one is the VRSI physical design. Okay, in this, okay, in this topic under VRSI design methodology, I will cover and emphasize more on the floor plan. Okay, uh, for floor plan is quite important. Okay, it is under physical design. Okay, this is quite important. Okay, but I will not cover it today. Okay, okay. Remember that a floor plan. Okay, never mind. I will mention about that later. Okay, I see that we only have less than 10 minutes. Okay, so now Let me see whether I should stop here. Because this floor plan topics, there are a lot to cover. Okay. Okay. Okay, maybe I will just cover a few slides only, then I stop. Okay, so about floor plan, what is floor plan? Okay, as you see here in this slide, okay, floor plan is the process of transforming a circuit descriptions into the physical layout, which describe the positions of cells and routes for the interconnections between them. Okay, before physical design, we have circuit design, logic design, and other some more. Okay, architectural design. Okay, okay. So all this is about the circuit. Okay, when we want to produce a physical design, it means that we want to transform a circuit description into physical layout. Okay, under physical layout, okay, there is another process. Another process. Okay, the process here, it has placement. Not placement. Okay, there is a diagram here. Okay, this is the diagram. Okay, these are the process: synthesis, placement, clock tree synthesis, signal routing, timer closure. Okay, all this process is under physical design. Okay, and the placements. Okay, all these placements is actually about the macro or cells placement. Okay, in a floor plan. Okay, so this diagram here, okay, they are related to this diagram. Okay, this diagram shows what it means by the placement and routing. Okay, so means that each of the process here, they perform certain steps. They have certain steps. They have the purpose. Okay, so all are stated here. Okay, so here um, okay, so later in Wednesday, okay, in this Wednesday, I will cover further about placements and routing, okay, in floor plan, okay. Floor plan is about the floor plan of the chip, okay. It is not floor plan of something else, okay. It is the floor plan of the chip, okay. Means that the the floor plan, okay, is it contains chips, input, output, macro, and others. Okay, like routing. Okay, routing can be signal routings or the power routing. Okay, so you see that this is the floor plan. Okay, it already show you here. Okay, this is floor plan, and then this is the macro. Okay, sometimes we call the macro as the blocks. Okay, and then there is a standard cells. Okay, this standard cells contains all the logic gates. Okay, or the logic circuit like multiplexer and what else? Multiplexer, demultiplexer, adders. Okay, so all these are composed of the logic gates. Okay, and then there is the input output pads. Okay, these whole things we call input output pads. Okay, these pads here is for the placements of the routing, for input output routing and to the power. Okay, okay, so I think I should stop here. Okay, Wednesday I will continue. Okay, Let me check your attendance first before we dismiss. Okay, I see that now in the Google Meet there are 28. Okay, later let me check. Who else? Four of you. Are you in the Google Meet now? No. How many of you not in the Google Meet? Two in. Or means two is not inside. Okay, okay, okay. So now 28 means there's 30. 30 minus 2 is 28. But the number is still not right. Okay, the attendance form that I received here is 29. Okay, I think I will check later. Okay, I have the Google record. Okay, later I will check who is in the Google Meet today. Okay, later I update your attendance. Okay, I have one announcement. Okay, for this week, Wednesday class, lecture class, I will go fully online. Okay, no need to come to class, for all of you. And then, okay, the reason why I want to go fully online, can you hear me? Jie, you can hear, is it? Can I? Okay. Uh, the reason why I go fully online is that we have like class, right? 4 to 6 on Wednesday. Okay, so I don't want you to go here and there. Okay, because I already mentioned to you practical class we need to go to fully online. Okay, so means that lecture class I want to go fully online so that we can do the class subsequently. Okay. Uh, okay, so for others, so for your noting, okay, we can dismiss class now. Later, we still have another tutorial class for group one. Okay, so for group one students, you have to stay back. Okay, thank you to all.